Hello and welcome everyone to the second last presentation of this multidisciplinary conference that we have. Hope you're comfortably seated by now and are ready to listen to what I have for you. So what do medical diagnostics, autopilots, and photo editing have in common? All these fields were highly revolutionized in the last few years by using artificial narrow intelligence or very specialized form of intelligence. But what about artificial general intelligence, where one agent can learn across multiple disciplines and learn how to perform a task in such a general setting? Current state-of-the-art artificial general intelligence, or AGIs for short, can already play computer games or predict text in conversation without being explicitly programmed with the rules of the environment. So we have artificial intelligence bots that can already play chess or Go with human level players. So can we apply this technique to do physics as well? I'm Aritra, and I will be presenting to you about how to build an autonomous quantum physicist. More specifically, we will look at quantum observers as evolving kinds of reinforcement learning agents. So basically, in this project, we will start off with a much more powerful form of intelligence, imbued in them with the essence of life, and try to discover the laws of quantum physics with it. It's like imagine you create an AI scientist and then retire for the rest of your life. Let the agent discover new laws of physics and progress human civilization from there on. So the first problem that we are going to look at is neural networks. So all the previous models that I talked about uses neural networks and trains them on data to understand the underlying laws. But there is a problem with neural networks that once you train a neural network, it is very hard to understand what is the underlying laws and what is basically the causation instead of the correlation of the output behavior. So for our models, we are going to use a different form of computation model, which is the Turing machine, which can encode any computer programs that you have on this red tape that you see over there. And once in the blue tape, you provide your input, the machine does some calculation and provides back the output in the blue tape again. So now you can ask that once you put this agent with this computing mechanism in some environment, what is the shortest red tape that you use? Or what is the smallest or the simplest hypothesis of that general environment? Well, that works good for induction. But we have another small problem. We want to map all of physics, right? So that includes quantum mechanics as well. And in quantum mechanics, we have the problem of a quantum observer. All of you might be familiar with the story of the Schrodinger cat, where you put a cat and some kind of a poison in a box and seal it shut. So as long as you're not opening the box, the cat might be both dead and alive. Once you open the box, you find that the cat is either dead or alive. So in this case, your act of observing or opening the box changes the fate of the cat. So in scientific terms, we call it as a participatory observer, where the observer cannot directly passively sense the environment. It needs to act, and every time it does some action, it changes the environment as well. So for our agent, intelligent agent who wants to understand the laws of quantum mechanics, we should have this mechanism. Thankfully, in artificial intelligence, there is already a technique called general reinforcement learning, which talks about an agent and an environment and an interaction between them. You can think of it like an active version of induction, where you just do not predict a passive future, but you also take into considerations what are the different actions that you can perform on this environment, and thereby leading to different futures. This model is called the ICSI model, which takes as a reward a perception from the environment, and then chooses the best action such that it maximizes the expected future return, as well as minimizes the hypothesis or the program of the environment. But what is a reward for our problems? We are not playing games. We are trying to model all of physics. And the environment is not going to give us a reward. So for our model, we set the reward passively as an introspect of what did happen in the past, how well our model predicted over time, and we give the reward to ourselves. The much bigger problem that we have over here is how many hypotheses do we consider? There are an infinite number of hypotheses, which gives the same input-output behavior. We can't expect to explore all of them. So we bound this hypothesis by additional parameters by the resources or the computational resources it takes to calculate them. These are energy, approximation, memory, and time, and we call it the least metric. So now instead of one parameter, the length, we now have 5 parameters. And we have absolutely no idea or a strategy to blend in these 5 parameters. So let's step back a bit and think of it philosophically. We as human beings did discover the laws of quantum physics, right? How did we do that? Maybe evolution and, well, Darwinian laws has some clue for us. Life is what is called evolves in an open-ended evolution. So we try to mutate and try out different strategies over time, and the best strategy survives. Maybe we can do the same thing with this model. We start off with a very simple strategy. We just add up all the 5 parameters that you saw in the last screen, and then let artificial agents evolve over time and produce different kinds of organisms, each with their own different strategies. So for example, we can have one strategy where we don't even need the green parameter, the one you see on the left with the frog. And then we evaluate the fitness of all these different models on how well they predict over time, and the best survives. So the best predictor survives. So now we have a strategy for our entire learning model, and we are implementing already all of these and trying to apply it on quantum experiments and trying to optimize them. So we have this agent, the one on the red, and we have an environment around it that it can sense the blue dots. Right now, we are working with very simple models where it's just the environment. And then we model a quantum circuit by which the environment evolves. And then we try to find out the perfect strategy by which the agent performs this experiment on a quantum computer. So we try to optimize and find the best strategy for the agent. In this case, is along this the green arrow over here. And that is the best way the agent can measure the environment. Of course, this work were based on the work of many pioneers in many interdisciplinary fields. Some of their names you can see listed over here. But the most important part is this work is far from over. We are in the need of enthusiastic individuals who want to join us in this project and help us create an autonomous quantum physicist. Thank you.